Hey folks, welcome to another video in this series on JAX. The previous video was about arrays, and now we will build upon that and look at the autograd system of JAX. So we will look at gradients. The key difference in how gradients are used in PyTorch versus the way they're used in JAX is that in JAX, gradients are not always computed all the time. So in PyTorch, every time you do a mathematical operation, PyTorch in the background creates a compute graph and it starts accumulating gradients for all the tensors involved in the computation. This is done by default every time you do a mathematical operation. The only way to stop it is to explicitly specify no grad or requires grad equals false. On the other hand, in JAX, gradients are not eagerly computed. Gradients are computed in a functional form. What I mean by that is that there is a function in grad that takes in your computation and then computes the gradient. So they are computed only when this function is called. So let's see how this looks like in JAX. Okay, so I have an example of a simple function. So I have here a function that returns x squared. It takes in a value and it returns the square of that. So to compute the grad, what we first do is we create a callable. So what I mean by that is we wrap our function using the new grad method that we import. So note, we first import from JAX, we import grad and then value and grad. We'll talk about these two functions, but grad computes the gradient and value and grad computes the value as well as the gradient. So it's like, it reduces your work. Okay, so we use the grad to wrap our function in and make it a callable. So df by dx, when I call it, it's like a function, we'll call the grad of f at the value x. So because gradients are evaluated at a particular point. Okay, so let's set the value of x to be 3 and we call this new callable with that value of x. So that should give us the gradient at x equals 3. So to double check that, we can just manually also compute. The derivative of x squared with respect to x is 2x and 2 times 3 is 6. So we should get 6. So this is the math here. When I run it, the function evaluated at 3 is 9 and the derivative is 6. So the expected value is 6. So okay, so grad computes the gradient of my computation, which is in this function, with respect to the variable of the function. So it's a bit confusing, but when you see a lot of examples, you'll get the hang of it. Okay, so let's now look at a different example. So one question you should have asked is, how does, if I have like multiple arguments, how would JAX know what gradient I need to compute? So let's define a new function. So here I define h, which is made of two variables, which takes in two variables and computes x squared plus 3xy plus y squared. Before we go further, an important note here is both this function, this h, and f return a value, or rather a scalar. And so this is the reason why is that gradients using this grad can only be computed on scalars. You can compute vector gradients or Jacobians or Hessians, but you need separate functions for that. Right now, we're only talking about scalar gradients. And I'll briefly talk about the other types of gradients, but so far, right now, all our functions will just return scalars. And this is the common thing in machine learning because you always compute loss as a single value. So, okay. So here, because I have two input, I want to compute the derivative with respect to both of them. And the way you do it is I create two callables and I specify what gradient I want and in this argnums format. So I specify argnums is 0, which will compute gradient with respect to the first parameter. Argnums equals 1, which will compute gradient with respect to second parameter. So I have two callables. And then when I want the values, I will call the two values or two callables at the respective x and y to compute the gradient. So let's run it. If you do the math, you'll see that the gradients are correct, and this is how you call you compute different gradients. Okay, so that's good, but let's look at the other function that we had, the value and grad. So okay, so again, I have my edge, which has two inputs, x and y. I don't know if I mentioned this already, but by default, argnums equals 0. So that's why in the first call, we didn't have to explicitly specify what argument we wanted derivative of against, because x, there's only one argument, and argnums equals 0 by default. That's why we got df over dx by default. Yeah. Okay, so we don't need to just define like separate callables for each input. We can also just pass in a tuple where I give in the list of a tuple of all my inputs, and this will compute gradients of everything. So here I compute gradient of my function with respect to both the variables in one go. So I create a callable, like a single callable, and I compute the value separately and the gradient separately. That's one way of doing it. But I can also compute the value and gradient together. So I use this value and grad, which is the import that we got earlier, to create a different kind of callable. And then when I call this callable, I get value and gradients together as like two results, two outputs rather. So let's see how this looks like. When I did it separately, the values were 11, and because the gradients will be a tuple because we passed in a tuple in argnums, so I get the derivatives of both in one go. And when I did value and grad, you get the same. Value and grad is more efficient because I don't need to run this compute two times. In one go, I get both the value and the gradient. So hopefully that makes sense. Okay, so let's look in machine learning context how all of this works. So you typically would have your loss function, which has a bunch of, your network has a bunch of parameters. You get some x, you get some y. So assume my parameter is a tuple with weights and biases. This is a simple linear regression. So I predict, I multiply my x with the weights at the bias, and then I equate that to the prediction, like I use a root mean squared error loss. And the reason we are doing this because it's linear regression. B, we want a scalar output. So we use some dummy data, x and y's, and basically we are modeling this y equals 2x, which you can kind of see. And the parameters, weights is 1, bias is 0, just the initial set of parameters. And we can compute, we use value and grad this time to compute both the value and the gradients. So because our parameters are packaged as a tuple, that's why we don't pass in any argnums. And this is the benefit of JAX because it can take in a tuple or a scalar or an array of values, more specifically pi tree of values. We'll talk about that later. And compute the derivatives with respect to everything that is packaged in this params. So we will see that the value of weights and biases are 1 and 0. The loss is 7.4. And the gradients with respect to both of them, because now gradients returns me a list of two elements for weight and for bias. And these are the values. And this is kind of like what you need for gradient descent. Okay, so now let's see how it looks for, let's say, a matrix. So here I have a matrix, or rather a matrix function, which takes in a matrix and computes the trace of the square of it. So here I compute the square, and then I compute the trace, or rather W times W transpose, and then the trace of it. Again, we do the same thing. We compute the value, we create a value and grad matrix callable, and then evaluate it at this particular value of W. Because there's no X and Y here, so we just compute the gradients with respect to W. And when we get the values, we will get like 4 gradients, because everything is packaged here as a list of lists, or rather an array. Again, Python lists don't work here, so you need to convert them into JAX arrays, which is what we talked about previous time. But there's only one argument, and we compute the derivative with respect to that argument, and that argument contains 4 numbers, and that's why we get a gradient matrix that contains 4 numbers. So now we get gradients of all of my matrix of W. Right? Hopefully that makes sense. If it doesn't, just stare at it for a minute. I'm sure you will get it. Okay, so now we will jump into some higher order derivatives. So what if you wanted to compute gradient or gradient square, or df by dx square, df by dx dy, second order derivative. So in that case, I can recursively, or I can repeat this wrapping. So remember, to create a gradient callable, we wrapped our function with the grad method. If I do it twice, I will create a second order derivative and a higher order derivative, and so on. So here I create basically, if I want first order derivative, I just wrap it once. If I wanted a second order derivative, I wrap it twice. So argnum over here is by default 0, so we are computing derivatives at x, of x, and here this shows that you can compute the second order derivatives, third order derivatives, and so on. So that's the cool thing. Like, you can keep wrapping your functions with grad to compute higher and higher and higher order derivatives. So pretty straightforward. Finally, I want to show you a simple gradient descent loop, like which because we're building up to LLMs and all that good stuff. So, or rather machine learning and LLMs and all that good stuff. So here, so we have like a rough train loop. I defined my parameters. So I have a mean squared error loss that we saw before, which the first argument is the parameters, which is packaged, x and y, and the loss. We create our function that computes the loss and grad by wrapping it by a value in grad function. And then we define our train loop, which takes in x, takes in y, learning rate, computes the loss, computes the gradients, modifies the weights and biases, like your gradient descent step, and returns the new thing. Then we start with some sample data, and every time we update our parameters with the new weights and biases. That's it. A pretty simple gradient descent loop. So let's do it. Step 1, W was 2, and then over the course of my gradient descent, loss is decreasing, weights are changing to whatever the optimized ones are, and yeah, and it seems to work. Let's see if I do it for 50. Oh, sorry. It is converging towards my target, which is 2 and 0. I say 2 and 0 because we have y equals 2x. So the gradient descent is converging. If I do 500, let's do that. Sorry. You can see that by 500 it has converged to the true value. So Yeah, a simple gradient descent loop that just works. Okay, next I will open up the documentation for the gradients and advanced functions related to gradients in JAX and just walk you through a few of the things that are just helpful to know about. Right, I'm on the advanced automatic differentiation page for JAX, and this has a lot of like advanced functionalities, particularly the ones pertaining to multivariate differentials and also Hessians. So the examples that we saw were pretty simple. It had scalar valued outputs, and the second order derivatives were also scalar. But in the multivariable case, your higher order derivatives could be matrices. So for example, here you could have like d squared f di dj. So it's a matrix ultimately for I and j. So your Hessian will be a matrix. And there are some efficient ways of doing it using Jacobian forward and then jax.grad. So this has a lot of details, but I'm not going to go into that because they're not really used that often until you're really using these higher order or Jacobian vector products. The other thing this also has is, hey, for some reason, if you want to stop the gradients during the gradient computation, you can use this function called jax.lax.stop_gradient for any particular parameter. And the reason why you might want to, so jax.lax, lax is a lower level primitive than jax, so it uses some lower level primitives, and that's why it's jax.lax. So you can read about it in this guide. The final thing is so Autograd works in two modes, forward and backward. You can read about it. There are tons of good videos about it. One is good for when your matrix is more skewed, like less columns than rows. The other one is good for the other case. But anyway, both are needed. So let's say if you have like a vector function which produces not a scalar, but a vector. So this function f maps from Rn to Rm. In that case, your derivative will be a matrix, right? Because it will be a matrix of output times input, because you're computing df, which is in Rm space, over the inputs, which is in Rn space. So it's a matrix of m cross n. For these, you typically use this Jacobian vector product. And this has some examples how you'll use them, but at least for the simple machine learning use case that we're targeting, you won't need them. But this has all the good stuff, a lot of details. So if you ever need them, just refer to this guide. And with this, I will end this video, and I will see you next time when we talked about VMAP and PMAP. All right, see you.